All right, welcome back to Chapter 2. We're picking up where we left off, Section 2.2, Graphs of equations in two variables, intercepts, and symmetry. Now, when you learned all of these things could be spread out over several courses, so it is kind of a reasonable review here. All right, objectives of this section: graph equations by plotting points. Now, they're going to be fairly simple equations for now, but this is a skill you're going to have to take with you outside of Chapter 2. In other words, never be afraid to graph by plotting points. It's amazing how students will learn that. Even in a short class like this, students will learn a skill, and they won't take it from Chapter 2 to Chapter 4. It's not... And that might even be, I don't know, something you might have done Chapter 2 just the day before. You're not allowed to forget Chapter 2 or the topics in Chapter 2, really anything. But the idea is make sure you're willing to use this, even when we're outside of this chapter, plotting points. Finding intercepts, definitely something we're interested outside of Chapter 2. Finding the intercepts from an equation. Testing for symmetry with respect to the x-axis, y-axis, and origin. We'll talk about that. And know how to graph key equations. I like to say that you should know how to graph every function. So when they say graph key equations, every function there is, you should remember its graph. There aren't that many functions in algebra. That we all just, when I say a function, I'm talking about, so buttons on your calculator. So the buttons on your calculator only involve one number. So addition is not a function because it takes two numbers. That's an operation. All right. So what functions are there? Well, there's square root. There's square. There's cube root, I suppose, right? Eventually we're going to talk about logarithm. Yeah, those are functions, and those are functions that you should know the graph. You should know the graph of every function. If you don't know the graph of a function, you don't know that function. By the way, probably the easiest function we have is y equals the absolute value of x. And yes, I'm saying you should know the graph of y equals absolute value of x, or y equals square root of x. And if no one told you this before, I'm telling you now, every function, you should know the graph. That's just where we are in math, where you need to know the graphs of of every function. They say key equations, I say every function. All right, let's get started. To graph by plotting points, I have my own take on this, but I'll just have this slide here so you can look at it. But let's go ahead and do a graph by plotting points. When I say I have my own take on it, I think of this as a machine that's made to find y. In other words, you can put in a value of x, and it's made to find y. So what am I going to do? I'm going to pick my x values. So I pick -2, -1, 0, 1, and 2, just like the book did down here. And then you don't have to show the calculations, but you want to calculate. So if I put in -2, I'd have -3 times -2, that's +6, plus 3, that's 9. And this is sometimes what I call a t-table. I'll just go ahead and write the other calculations down here. And for me, a t-table like this, I call it a t-table because the letter T is kind of there before I put anything in there, is giving me all the information that they were giving me here. So go ahead and make a table. Now, if you're going to graph this, it doesn't hurt to give these letters a name, each point a name. A, B, C, D, E, nothing terribly. Let me go ahead and write them here. A, B, C, D, E. I see the way this is done here as kind of the formal way of doing it, but making a table. And keep in mind, I picked my x values and calculated my y values. That's the key for point plotting. Now, if we're going to graph this, reason why I put my letters there is, I don't know, I think it gives me a little more information if I incorporate the letters here. This isn't something you're going to need to do on a regular basis, but put the letters next to the points. And then, as they did here, we want to draw a line through all of those points. Now, why are we drawing a line through those points? Why not some other kind of curve? Well, we'll get to that. But you have to know the shape of what you're drawing for something like this to make sense. I'll go ahead and just say it. We will get to it, but y equals mx plus b. If it has this format where m is revealed in the problem, b is revealed when you get the problem, you know the figure is going to be a line. And if it's not y equals mx plus b, or it can't be manipulated into y equals mx plus b, you have to consider it might not be a line. It'd probably be some other shape. All right. Now keep in mind, a lot of what we're doing here is not visual. It's based on a calculation. So, how would you tell somebody over the phone where the intercept of something is? Not that you would ever do that, but how would you, without a picture, without a way of giving somebody a picture, if you were both in a dark room and you wanted to talk about the intercept, you can find it and you can describe it very, very accurately. And that's our goal here. It's not just to draw something, it's also to describe it. So this problem they didn't really ask, but this is the y-intercept, and this point is the x-intercept. And we can see the ordered pairs for it. And one of the things you'll notice for the intercepts is, for the y-intercept, the x component is 0, 0,3, and for the y-intercept, for the x-intercept rather, the y value is 0. And that's going to be an important calculation technique later. So we don't just want to analyze intercept, and this is unique to this class. If you took algebra classes before, they probably didn't make a big deal about whether a point touches or crosses. And right now they're not distinguishing, but they're just saying that if a graph touches or crosses the axes, it's considered an intercept. X-axis versus y-axis, but I kind of talked about that. So here is a image right out of a future chapter in our book, because we do talk about an intercept, whether it touches the x-axis, means it didn't change quadrants here. It stayed in the quadrant it was in. It crosses here, crosses here, crosses here. So there's 1, 2, 3, 4 intercepts, 3 x-intercepts, 1 y-intercept. All right. And the intercepts are points that can be expressed as ordered pairs, and that's going to be important to us. Finding the intercepts. All right, well, that's what they're asking you to do here, just finding the ordered pairs. Now, this is a quirk both in the book and on the website, so let me give you this tip right now. When the book and the website talk about intercepts without a letter, if it just says intercepts, they will give you the entirety of that intercept. They'll give you the parenthesis, the minus, the 4, the comma, and the 0. The word intercepts means we want what I call the 5 parts of the answer. The 5 parts are the parentheses, the comma, the x value and the y value. So do that. Now, they don't do that when they say the x-intercepts. This is pretty specific to our book. I don't think other books necessarily adopt the same exact format, but when they say x-intercepts, they just want the number from the ordered pair that's before the comma, the x value. They just want the x value. If it says x-intercepts, not just intercepts, but the letter x, character x is there, then just express it with the x value. The y-intercept, just express it with this value. Now I'm saying that this might not carry over into your next class. So in other words, you may have a teacher who would mark -3 for the question, what is the y-intercept? Mark this wrong and say, no, I wanted you to say 0, -3. I wanted the whole thing. But our book is consistent and the website's consistent. When they ask for the y-intercept, they only want the y value. They just assume everybody knows that x is 0 for the y-intercept. You don't have to give that extra information. All right, so what was I saying? How do you find the intercept without peeking, without looking, without seeing the problem? Well, you find the x-intercept by letting y equal 0, and you find the y-intercept by letting x equal 0. And that's about it. That's how you do it. So we were given this equation, y equals x squared minus 9, and they're saying find the graph. I'm not, even if we didn't want to find the graph, if the question were to find the intercepts, you would let y equal 0. So see how y is this entire side. So they let that side equal 0. Solved it by factoring and got x-intercepts of 3 and -3. All right, that's the x-intercepts. Next step, let's find the y-intercept. Now, when they say y-intercepts, it's usually just one. I'm not going to say it's always one y-intercept, but because of something called the vertical line test, expect one intercept for most of the graphs we do. But we're just going to replace x with 0. And what do we get? Y equals -9. So understand, we know a lot about this graph already. We know that here at -9, there's a y-intercept. At -3 and at +3, there are x-intercepts. And hopefully, we know the shape of the base graph, y equals x squared, because remember how this problem started. It was y equals x squared minus 9. Let's look at it here. Y equals x squared minus 9. Yeah. So it's going to have the same shape as y equals x squared. All right. So let's look at they actually did a little more work with this. They graphed it. They plotted more points. But there are our intercepts and a few extra points. And you can see we got this parabola. All right, this might be a little new to some of you, this idea of symmetry. And the idea here is there's a very simple test, sometimes called the sign test, that will tell you if about the symmetry of a graph, or will test to see if a graph is symmetric. We say test for symmetry with respect to something. Symmetry with respect to, well, you can have symmetry with respect to the x-axis, means the points are on both sides of the x-axis. You have symmetry with respect to the y-axis, meaning they're equally far from the y-axis. And there's one other symmetry we'll talk about. But this is the idea for symmetry with respect to the y-axis. So they're saying this point and this point are symmetric with respect to the y-axis because, now that's very important, because the y values are the same, but the x values are on opposite sides of the y-axis. So we have symmetry with respect to the y-axis if one of the x values is whatever x is and the other one is minus x. So symmetry with respect to the y-axis. This can actually help us. So let's go on to this one. So it's saying if a graph is symmetric with respect to the y-axis and it contains this point, it's also going to contain this point right here. And now that's visually true. I mean, it's true just looking at it, but even before I drew it, I knew that if somehow I knew the graph was symmetric with the y-axis, I would have this point A, and I'd have this point, I'll call it A with a little tick mark, A prime, because it is, well, if it's symmetric, that must happen. All right, the other kind of symmetry we are going to talk about is symmetric with respect to the origin. So this point right here is the origin, and there are some very important graphs that are symmetric with respect to the origin. And what that means is if you have a point x comma y, you'll have, if I call that A, you'll have its symmetric point minus x comma minus y. If I call this point B, this point could be the symmetric point, where you just change the signs of the values. Symmetry with respect to the origin. All right, so in this case, if I have a point symmetric, if I have this point, and they're telling me that it's symmetric with respect to the origin, I'd also have to have this point. Let's see, is that 3? Yeah. Also have this point. So you kind of think of this as if you're going to connect one point to the other, you'd go through the origin, and the origin would be the midpoint. And that's kind of what makes it symmetrical, meaning if they're both looking at each other, they're both about the same. They're both same distance from that point. So symmetry with respect to the origin. So our tests for symmetry are algebraic, not geometric. In other words, in this class, you don't just say it looks symmetric. You replace y with minus y and see if you get the same thing you started with. You can test for symmetry, replace x with minus x and see if you get the same thing you started with. Or for symmetry with respect to origin, you do both. So here's a problem where they're going to test for symmetry. And what are they going to do? For the x-axis, remember for the x-axis, the other letter, they're going to replace y with minus y and see if you get the same exact equation. And the thing is you don't, because this equation right here with y replaced with minus y is not the same as the original equation, right? This has a minus sign that doesn't go away. This one doesn't have a minus sign in it. They're not the same. So that means the graph is not symmetric with respect to the x-axis, which might help us in terms of graphing. This is a pretty quick test. Replace the x's with minus x's. Because both the x's were squared, a pretty straightforward simplification means it takes me right back to what I originally had. So the graph is symmetric with respect to the y-axis. And the last one they did was symmetry with respect to the origin. So they did a double replacement here. And the minus sign's still there, so not symmetric with respect to the origin. And debating whether to stop. I'm going to go ahead and stop. All right. So I'm going to stop here just for recording length, and we'll pick up here next time.